Hello, and welcome back to Learn It From a Layman. We have today Cameron back again as the trusty member of our crew that doesn't, leave us. So, but we also have Matt, who has rejoined us after a long absence. That means you no longer hate us. I'm taking from the silence.
Add some witty commentary here. Yeah, you summed it up about correctly.
Okay, good. All right, and Matt's back for
the foreseeable future.
Yes, exactly. So, and then we did kick Tim off because who needs him? And we also gave him a virus. So take that, Tim.
Stomach virus. It will get you every time.
All right. Well, today we're going to be discussing the basics of physics. And I can tell you that from my perspective, I'll probably learn something today. So that will be something accomplished, if only from Wikipedia.
Wikipedia accomplishes nothing.
I donate to Wikipedia. Dang it.
Really? You donate?
I absolutely donate to Wikipedia. So.
Wow, you're a much better person than me.
Okay, now getting back to physics. All right, so physics is one of those classes I never took in school, literally at all, not a single time. So what I'm going to share today is well beyond what I probably should, given my complete lack of knowledge. But we're going to start with the basics, and that is going to be some of the history of physics. And so we'll start with Isaac Newton. So, Cameron, enlighten us on what Isaac Newton did.
I'm pretty sure most of what I know about Isaac Newton is fallacy. So what I'm going to go with is he was a man.
Good.
He lived back in the day, I want to say 14th century. Who knows?
Make some number up, yeah.
He was a mathematician. Matthew is talking and we can't hear him.
That's also true.
Sorry, so Isaac Newton lived from 1642 to roughly 1726 or maybe 7. Date of death is a little uncertain.
So 16th through 17th century.
17th and 18th, but
whatever.
Regardless.
Yeah, we're talking about physics, not century numbering. So.
He was a mathematician and most famous for his gravity theories. And I think the fallacy was the apple on his head. Apple on his head and help give him the idea of how gravity works. So.
Yeah, I read something about that that's not exactly how it happened. And anyway, he did come up also with calculus, but let's not hold that against him. Everyone slips up and invents another branch of math occasionally. But he did do lots of good things, as Cameron mentioned, as far as describing the way that we understand the world, the universe, motion, gravity. And so let's talk about his 3 laws of motion, which I think are kind of the first things you learn in physics, though I wouldn't know because I don't know the first thing about physics. So, Matt,
before we go too far, I will point out that Isaac Newton and the Newton family has what is possibly the most metal coat of arms of all time. It is simply a black shield with white crossbones.
Wait, is that the pirate?
Pretty close. Doesn't have the skull, but it doesn't need the skull because they're just that cool.
Is that the first?
Yeah, the first. Yeah, well, and it plays into Newton's first law of everything, which is that the more hardcore your shield, the better the scientist you are.
That's what I remember learning.
Right.
Wow.
So, yeah, as you guys mentioned, Newton is known for a number of things, and he actually contributed a huge amount to almost all the fields of physics and that branch of science. And physics encompasses a lot: motion, gravitation, all of the forces of nature, light, electromagnetic waves, He was the one that realized that you can split light with a prism and then recombine it, and that sunlight actually carries in it all the colors. And yeah, he was kind of the first one to come up with, to realize that that was a thing. But his laws of motion are, a lot of people are familiar with the fact that Newton had some laws of motion, but very few people know what they are. So I will zip through those really quick if you like. I can give you kind of the layman overview without quoting directly from Wikipedia.
All right.
All right. So the first law of motion, every body persists in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. Simply
That
put,
wasn't layman.
an object at rest will remain at rest, and an object in motion will remain in motion, unless another force is brought to bear on that object. So if your thing is not moving, it is not going to start moving unless you push on it. And if it is moving, it will not stop moving unless something pushes back against it. That is his first law of motion. In practice, when you think of a car, your car is moving, right? And if you take your foot off the accelerator, it will eventually come to a stop. But you need to understand that there are always forces acting against your car. Friction from the road, air resistance, friction from the internal mechanics and mechanisms in your engine, and so forth. But if you imagine a car moving on a frictionless surface, or a better example, imagine that little plastic puck moving on an air hockey table. If it starts moving, it's not going to stop moving until it bumps into something. So that's Newton's first law. If your thing is not moving, nothing's going to start it moving until you apply a force to it. And if it is moving, it's going to keep going until another force stops it. Any questions?
Like the force.
Yes. Newton basically...
he was a Jedi.
It would have been good if he had been able to become aware of the Jedi Order.
Yeah, I
but
think so.
That would have just elevated him to a level of knowledge that humans aren't supposed to be able to attain. And
well, you did mention that
would have
his
thrown
death,
the universe out of balance.
You mentioned his death date is uncertain, so there is the possibility that he became a Jedi ghost, right? So
I feel like this is derailed in weird ways.
All right. Good. I'm glad.
Newton's second law of motion is the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. And it's impressed with an apostrophe D, which is a little weird, whatever. All that says is that if your motion is going to change, it will change in proportion to the force that you put on it. If you apply a light force, you will apply a small change to motion. If you apply a large force, you will apply a large change to motion. So, if you are driving down the freeway in your car at a constant speed, not changing your acceleration, your car is in motion, and it swats right into a bug, that bug is going to apply a small force to your car, so small that it won't really be noticeable. If you apply the force of an unfortunate bird to your windshield, you'll apply a little more force, you'll hear it, it'll make a sickening thunk, but it's not going to change the motion of your car too much. If you apply a larger force in the form of a Utah mule deer to your windshield, that will cause a significant change in the motion of your car. It will cause a negative acceleration. And if you apply a larger force, like a Wyoming buffalo, to the front of your car while it is in motion, it will apply an even greater negative acceleration, and you will definitely feel that. And finally, if you apply an overwhelming force, like a brick wall, to the windshield of your car as it is in motion, then you will see a nearly instantaneous change in that object's motion or velocity. It will go from moving to not moving because the force is so much higher. That's all the second law says. Any change in motion is relative to the amount of force that you put on it. practical application in my world. You have a satellite, and you want it to move very quickly. You have to use a large thruster to move it quickly. If you want it to move not very quickly, then you use a small thruster.
I have a question.
Yes.
Okay, so I may be reading Wikipedia right now, because I have no idea. But it says there are two variables: the mass of the that determine, this. So it says the mass of the object and the force of the object that are acting upon the other object.
Mm-hmm.
So, how does what? I understand force.
Yep.
But aren't force and mass essentially two sides of the same coin?
No. Turns out they're not even close. But it's a good thing that we are having this podcast, because that is what your layman would think.
No. Mass would be like you have a semi and the force is going, let's say, 70 miles down the road. And then let's say you have a car, which is another mass, going 70 miles down the road. They're going at the same force, but not the same mass.
Okay.
And then if the semi hits the car, its greater mass will crumple the car.
Something like that, but there's more to it. And I don't know how quickly you want to jump into standard units. The equation that comes into play is force equals mass times acceleration.
Right. I heard about that.
Yeah, indeed. F equals
F
ma.
equals ma.
So, if you're in motion and you're not changing your motion, according to Newton's first law of motion, when you're just cruising along and there's no other forces in play, then your acceleration is 0. Your velocity is whatever it is, say 60 miles an hour. But in the absence of any other force, pretend there's no friction, pretend there's no air resistance, pretend there's no mule deer, your acceleration is 0 because you're not changing your speed. So the force being applied to you is also 0. F equals ma. 0 equals the mass of your car, say, 3,000 kilograms, times the acceleration, which is 0. Now, if you want to change the acceleration of your car, your 3,000 kilogram car, and you want to change it by 3,000 meters per second squared, then you would need to apply a very large force. Your force would equal 3,000 kilograms times 3,000 meters per second squared would equal 9 times 10 to the 6th newtons, which is a bunch of newtons.
That is like figs?
Yes, exactly.
Okay.
It would take a large force. Now, imagine instead of your 3,000 kilogram car, you have your 30 kilogram child. It's charging down the hall, and you want to bring it to an abrupt stop. You don't need to apply nearly the same amount of force, like, a fleet of mule deer to your child to stop it from running down the hall as you would to your car. So the two variables, mass, acceleration, really 3 variables, mass, acceleration, and force, they all just change on how quickly you want the acceleration to change and the mass of the object that you're starting with. A heavy mass is going to take more force to bring about a large change in acceleration than would a small mass. And that has to do with inertia.
Okay, so actually, you know what? We'll come back to this because I have more questions about measurements of force and how that works. But
why do they have silly names?
Newtons? Oh, they named them force units Newtons because, Newton. Also, they were impressed with his family crest. But anyway, back to what Carl was saying. What?
Well, I have questions about how you measure force independent of mass. Is it? But, okay, let's come to that in a minute. Let's do the third law of motion, and then we can circle back on this.
Excellent. Okay, the third law of motion reads, as Newton wrote it, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So what that says is anytime that you apply a force to a thing, the thing applies a force back to you. So when you push on your car to get it moving because you've let it run out of fuel in the middle of the street and you need to get it out of the way, you push and you push and you push, and the car slowly starts to move. But you do not fall through the car. You do not you cannot move through it as you would if the car was not there, because the car pushes back on you. Likewise, to my knowledge, none of us have ever fallen through a solid floor.
Well, Cameron, wait, hold on. Cameron? Can we confirm?
Okay. Anyway, to my knowledge...
Yes, I have fallen through a roof.
All right.
Okay, well, that's different. Roofs are in their own branch of physics entirely.
Exactly.
So we apply a force to the floor every second because gravity is pulling down on us. We apply a force equal to the acceleration of gravity, 9.81 meters per second squared, times our mass, which for me is a svelte number of kilograms. But the reason I don't fall through the floor is because the floor pushes back on me with an equal force. That's what Newton is saying. Anytime a force is brought into play between two objects, that force is directed against both objects in opposite directions.
So if I fall down, the Earth comes up to meet me. I don't meet the Earth. Is that what you're saying?
No, not at all, actually.
I think that's what you just said.
What I am saying is that if you fall down, your entire body will hit the floor. And you will not go through the floor, because the floor, as you crunch down on it, the floor will push back on you, preventing you from going through the floor. Another example that might help illustrate this is imagine an astronaut floating about in space. He takes off his glove because he's not very smart, and he chucks it just clear out into the void. When he throws the glove moves away from him, right? Does he move away from his original position?
Yes.
Yes, he does. He does not move as fast because his mass is larger, but the same force that he applies to the glove applies to him. And because F equals ma, the mass of the glove is smaller, the acceleration from that same force for the glove will be larger. The astronaut having a larger mass, his acceleration will be slower, but he will accelerate. And so if you can imagine the astronaut is at his original point, he throws the glove zips off to the left of your screen at a very fast speed, but your astronaut will start floating to the right of your screen at a much slower speed. But he will be moving. That's Newton's third law of motion. Every action has an equal and opposite reaction. Equal in terms of force, which will apply a different acceleration based on the mass of the two objects. Anyway, any questions on that?
That just sounds like what I just said. If I'm not pushing on the ground comes back up to meet me.
Yes.
So if I'm falling, the Earth comes up. I don't fall down.
Yeah, let's just say yes and move on.
I do think that I have evidence to the contrary. I've seen lots, like the movie Gravity, for example.
Yeah, okay.
I've heard that was 100% accurate in all ways. And
you know what? For most laymen, it is, and it is just a scientific treatise dripping with insight on the workings of orbital mechanics and relative motion and how to kill George Clooney using science.
Yes.
But
okay,
sarcasm off.
Yes. Okay. So that makes sense. So we already started talking. Okay, so those are the three laws of motions. Let's move on quickly to Einstein. So
we'll just cover this quick.
Yeah, exactly. We'll jump on to Einstein really quick. I'm sure we're skipping over a number of physicists that deserve to have their name mentioned, but they won't have their name mentioned by me. So,
wow.
Well, sorry, guys and girls. Okay. Einstein, from what I understand, so I'll give you from the layman perspective first. Einstein versus Newton. Einstein essentially went. It's a different way of understanding. It's a whole different like paradigm on the universe than Newton, from what I understand. Einstein kind of the macro, where Newton is the Einstein is the micro, where Newton is the macro, right? That's kind of my layman's understanding, is that when you're talking about Einstein, you're talking about, you know, boundary conditions, small things. And once again, I understand that it's kind of a bigger, it all fits into the bigger theory of relativity and all of his other insights into mathematics and physics, but that's the layman's understanding. If I had to compare Einstein and Newton, is that Einstein talks his description of the universe covers a lot more boundary conditions, and as far as application to everyday physics, we still use Newton's laws by and large. Is that more or less correct?
No, the layman is way off in that understanding.
Well, good. Glad to be corrected.
Excellent. So how to explain this? Because I, being a layman myself, right, I definitely get lost with some of Einstein's stuff. Basically, Newtonian mechanics do govern what you would have on Earth. When you get to the workings of the universe at large, that's where you get into Einsteinian mechanics. Now, going down the other direction, when you go down to the really micro, to the atomic and the subatomic, there you get into dark magic realms that the bridge between micromechanics, really quantum mechanics, and Newtonian mechanics doesn't exist yet. It's not understood. In fact, it has been said by a wise man, meaning, my dad, that the next Einstein will be the person that can create that bridge between Newton's mechanics for everyday motion and the quantum mechanics of subatomic particles. But Einstein, when you look at some of the more famous theories that he is known for, the theory of relativity, general relativity and special relativity, those have to do much more with the workings of the larger universe, in my own opinion, which is probably also wrong, but whatever. A lot of, and again, I'm going to get really lost here. I cannot give you a simple description of the theory of relativity, because it's not simple, it's hard. And Einstein did so much more than just the theory of relativity.
Sure.
He's one of the layman misconceptions is that E equals mc squared is a relativity equation. It's not. They're sort of kind of related in the sense of all physics in the universe is related. But E equals mc squared has to do with mass energy equivalence, not necessarily relativity. Relativity has to do with motion in different frames of reference, and in particular the speed of light. And I'm going to try to describe this as best I can, because again, I get lost here. But he had two theories of relativity. There is the special theory of relativity, which in my opinion is actually more your everyday theory of relativity. And then he had the general theory of relativity. And the difference is how the two account for gravitation. Special relativity does not really account for gravitation, where general relativity does. General relativity means that it is applicable in all situations because it accounts for gravitation. But in the special theory of relativity, how to sum this up in a very succinct way? I don't know.
All right. That's the
Would
layman's
one
answer.
be better for space, and one would be better on a large celestial body?
Well, those are both in space.
No, inside a large celestial body. Because in space there's no gravity.
Wait, what? No, there's definitely gravity in space. Newton figured that out. But
there's gravity in space?
yes. I mean, well, okay, so jumping into a tangent. Yeah. Gravity exists between every object in the universe. And there is a gravitational equation. The force of gravity, G, is equal to some constant that I forgot, times the mass of the two objects combined, divided by the distance between those objects squared. So if you have the sun and Earth, each one has a mass. You add those masses together, you multiply it by that ridiculous constant that I've forgotten, and then you divide it by the distance between the Earth and the sun squared, and that gives you the force of gravity between those two objects. That force equation applies to every object in the universe in relation to every object in the universe. So me sitting here at my computer, there is a force being applied by every individual key on my keyboard and my monitor and my desk and my chair and my mouse and everything to me, and I'm applying an equal force to it. It is so infinitesimally small that we don't notice it, but it is there. One of the layman ways to think of gravity and the relative impacts of gravity on different objects is, imagine that every object in the universe is resting on a really flexible rubber sheet. And if you have a massive object like the sun, it will make a very large depression in that rubber sheet, and every object on that sheet will roll towards it. A smaller, less massive object will make a smaller impression on that sheet, but it will make an impression. And the further away you are from that impression, the less effect it will have, but the closer you are, the greater the effect it will have.
Okay, so this is part that. So when I say this is one of the big differences between what Einstein theorized and what Newton understood was essentially the way that gravity works, right? Like what you're describing, right? It's one thing to be able to describe and measure gravity. It's another thing to be able to fit gravity inside of a greater theory of curved space-time.
Well, yeah, kind of, sort of. So the equation that I gave you, that equation I gave you is a Newtonian gravitational equation.
Right.
Einstein didn't really, as my understanding is that his equations don't necessarily have to do with gravitational forces, but they have to do with how they do touch on how gravity affects everything else in other weird ways, meaning, well, time, how gravity and time relate.
Right.
So one of the big things with Einstein's theory of relativity that just blows people's minds, including my own, is imagine that you are on the freeway, on I-15, traveling to wherever you're going. And you're going along at 95 miles an hour because you're a renegade and that's how you roll. The highway patroller that is chasing you down is closing on you, and he is traveling at 120 miles an hour. What is your relative speed to that highway patroller? If he's going 120 and you're going 95, he is closing on you at a relative speed of 25 miles an hour. Now, the highway patroller in the other lane, who is coming to intercept you, also going 120 miles an hour, is moving relative to you at a much faster speed. He's moving at 120 plus 95 miles an hour. So that's what, 220 miles an hour? Something like that? Yeah. So that's just very basic relative motion. Now, here's where you start to destroy minds. Imagine that you shine a light from your car moving at 95 miles an hour towards the back of a truck in front of you that is also moving at 95 miles an hour. The light hits that truck at the speed of light, right?
Sure.
Okay. Now, imagine that you shine a light at the highway patroller in the other lane who is moving to intercept you, who is coming towards you. Imagine at the same time that he shines a light back at you. What is the closing speed of the two beams of light? You're shining light at him, and that beam is moving at the speed of light. He's shining light at you, and that beam is moving at the speed of light. The relative closing speed of those two beams of light is...
Twice the speed of light?
It is not. It is the speed of light.
So it's just a constant. I mean, the speed of light is like saying infinity, right? It's like...
No, it is not. The speed of light is not infinity. It is 3 times 10 to the 8 meters per second.
Look, I know that we can measure the speed of light, but
Yes.
but for all intents and purposes, it is the speed limit of the universe.
It is the
right?
speed limit of the universe, and that's kind of what Einstein is saying, that no relative motion can exist faster than the speed of light. So if I shine two lights at each other, their beams close on each other at...
The speed of light.
Not 2 times the speed of light, which is utterly contrary to classical mechanics. And so in order to explain that away, you go into some weird reactions with how time changes based on how fast you're moving. Whereas when you approach the speed of light, time slows down. And so that may help you explain, maybe, I still don't really understand this, that relative motion between those two light beams. Say I'm riding on that first beam of light. I'm traveling at 3 times 10 to the 8th meters per second. I'm zipping along pretty quick. And I see a beam of light coming at me just that fast. The reason I don't see that coming at 2 times the speed of light is because, for me, time has actually slowed down a corresponding amount. Again, you start to destroy brains here with this.
Will I see my reflection if I'm going at the speed of light?
Yeah, you will, which is weird, but you will.
Good
and
times.
So that's kind of, I believe that's one of the postulates of Einstein's special theory of relativity. It is easier, for me at least, to talk about what the theories mean rather than what the theories are. So for what's up?
Well, I was going to say, I do have one other. Once we're done with this topic, I have one other thing that because I mentioned the speed of light being the
speed limit of the universe.
Speed limit of the universe. I have one counter example.
Okay, sure.
But
Star Trek.
And no, it doesn't come from an Arnold Schwarzenegger movie or Dwayne "The Rock" Johnson. But I'm sure he could if he wanted to. So,
well, before we move on, I'll mention one thing. I mentioned E equals mc squared. That is actually a consequence of the theory of relativity. And I won't go into how, but basically that equation states that energy and mass are equivalent and can change from one to the other. That doesn't sound like it should be a thing, right? You're either a thing or you're energy, not both. Well, that's true, but you can move from one to the other. In fact, when we dropped the nuclear weapons on Hiroshima and Nagasaki, the atomic weapon that we dropped on Hiroshima, part of it was so powerful. During that detonation, roughly 0.7, that's less than a sheet of paper, grams of matter were converted to energy. And that's what created that massive nuclear explosion. The fact that matter became energy in that reaction. 0.7 grams leveled that city. So that and it does so according to that equation. Energy equals the mass of the object times c, the speed of light squared. Anyway, that's that. I'm happy to move on or have you edit that out, whatever you want to do.
No, that's interesting. Yeah, I think all of this has been very informative to me because, like I said, if I know about as much as Cameron's dog that he just held up about physics.
Wow. Gonna take
Science is scary.
Let's just say I was a humanities major, so we. To be fair to me, which I am a lot, I did take a computer science class that did have me do mathematical proofs. So that was at least useful, though it's not in the realm of physics. But okay, so one, oh, yes, hi Suki. The dog is waving at us. We got to lighten things up here, right? I'm sure there's some minds out there that have been melted.
I think mine was. I've taken physics, and I still don't understand physics.
Okay, but the one interesting thing I wanted to mention as far as speed of light goes, is so away from mass being converted into energy, which is its own interesting topic. And we visited this actually in one of our podcasts from months and months back, but around a black hole, the way that space-time warps, you actually can have objects traveling faster than the speed of light, but that is actually because space itself is traveling faster than the speed of light, is my understanding. At least that is the theory. Obviously, most of our understanding of black holes is theoretical, but the theory is that around black holes, the gravity becomes so enormous that space itself is literally pulled along at a speed greater than that of light. And so objects inside of it can obviously then travel whatever speed. I mean, there's literally no way to describe it at that point. I read an article about
that where they're going with in that one movie that time just slows down to some crazy amount.
That was an interesting movie. That was
Interstellar.
Interstellar. Yeah, that one.
Yeah. So I haven't heard the one about what you just said, with space distorting faster at a rate faster than the speed of light, but it is within, I believe it's the general relativity theory. Gravitational time dilation is part of the general theory of relativity, Einstein's general theory. And basically it says that clocks run slower in deeper gravitational wells. I don't know if that really addresses space being warped and pulled at a rate faster than the speed of light, but what it does say is that the deeper the gravity well, the slower time moves.
I remember discussing this with our cousin, right? Didn't we?
Yeah, we did this, and it went into weird areas.
Rabbits, I believe.
Basically, what had been said in that discussion, as I recall, is that if you chuck someone into a black hole, you will see them vanish immediately. But from their perspective, they'll be falling for eternity and never really move from the cusp of that black hole. Just because time slows down for them to such a ridiculous extent. They will see time chug along as per normal. But their time frame will be slowed so much more than ours that from their perspective, they'll never move. So, which is a horrifying thought.
So will they not age? Can you live forever if you go down a black hole?
Actually, you're right, and that's not a horrifying thought. That's an amazing thought. So basically, we're not talking about the fountain of youth. We're talking about the gravitational well of youth.
There we go.
Mortality is just to chuck yourself into a black hole. And you will live... Well, so here's the problem. For you, you'll still age and die. I guess. It's just that the entire universe will crumble around you and probably suffer heat death before that happens.
Right. Okay.
Well, that is a great way to finish our podcast, I think. I've always wanted to end our podcast with the death of the universe, and I guess
there it is.
This is the way to do it. Okay, well, I have been edified and generally confused, which was kind of the hope going in here. So I can now sleep either incredibly well or not at all, as I ponder whether or not I would die being sucked into the gravity of a black hole.
Well, and if any of our many listeners have any questions about it, feel free to contact me at timothy.cox@mesa.edu. So,
yes, Tim will certainly give you great insight into physics, insight that you have never heard of and will never hear again. So go ahead and email Tim. Just to give us an update on our listeners, we are worldwide. We have recently had, I believe, our first listener in Sweden. So welcome the Swedish audience. I won't say the few words in Swedish I know because they're all curse words.
Poor Swedish guy. Who's listening to us there?
I don't know. It's dark up there, so they find some mode of entertainment. Okay. Anyway, so welcome back, Matt, and we will continue our podcast again in the near future with some topic that will probably not melt your minds in the same fashion, hopefully. Though if Tim's back, maybe it will. Until
for
then,
a different reason.
Until then, we'll see you next episode.